value of x. To do this, I think I want to begin where I did with the piecewise function that we looked at last time, and just observe that since f of x equals x, if x is greater than or equal to 0, and negative x if x is less than 0, we can define f prime on the open interval from 0 to positive infinity, and on the open interval from negative infinity to 0, as being the derivatives of these expressions, and these are linear expressions. So we really don't have to work too hard to come up with the derivatives of these linear expressions. F prime of x equals something if x is greater than 0, something else if x is less than 0, and if x is equal to 0, that's going to be left for us to figure out. So if x is greater than 0, the slope of the tangent line is going to be the slope of this piece of the graph, which is what? 1. The slope of the line y equals x is 1. If x is less than 0, the value of the derivative is going to be the slope of this piece of the graph, which is negative 1. The slope of y equals negative x is negative 1. So negative 1. But I can't just get the derivative at 0, because 0 is not inside of either one of these open intervals. It's not in the open interval from 0 to positive infinity or from negative infinity to 0. It's an endpoint. So we have to do it like this. If it exists, f prime of 0 would be the limit as delta x approaches 0 of f of 0 plus delta x minus f of 0 all over delta x. That's the definition of derivative if it exists, if the limit exists. And what we'll see is that it's not going to exist. So to evaluate this, I'm going to simplify a little bit, and then we'll see that we need to consider the two one-sided limits as delta x approaches 0 from the left and as delta x approaches 0 from the right. So let's see, the limit as delta x approaches 0 of, f of 0 plus delta x, let's go ahead and say that's the absolute value of delta x minus the absolute value of 0 over delta x. The absolute value of 0 is 0, certainly. So maybe just say the limit as delta x approaches 0 of the absolute value of delta x, absolute value of delta x over delta x. Now, to evaluate the absolute value of delta x, we have to know, is delta x positive or is delta x negative? If delta x is positive, then it's just delta x. But if delta x is negative, it's not delta x, because the absolute value can't be negative. It's got to be the opposite of delta x. So to figure this out, we consider the limit of the absolute value of delta x over delta x as delta x approaches 0 from the left, and the limit of absolute value of delta x over delta x as delta x approaches 0 from the right, to evaluate this limit. If they both exist and are equal, we'll declare the two-sided limit to be equal to their common value. If they both exist but are not equal, then the two-sided limit will fail to exist. Now, if delta x is a little bit less than 0, then it's negative. And the absolute value of a negative number is the opposite of that negative number. So this equals the limit as delta x approaches 0 from the left of the negative of, the opposite of, I should say, delta x over delta x. Have to know if delta x is positive or negative before I can remove the absolute value bars. But now that we know it's negative, we can remove the absolute value bars and write it. So this is the limit as delta x approaches 0 from the left of -1, and the limit of a constant is that constant. So -1. Over here, this equals the limit as delta x approaches 0 from the right. Now, delta x is a little bit to the right of 0, so it's positive. So the absolute value of a positive number is just that number. So we lose the absolute value bars and write delta x. So this is the limit as delta x approaches 0 from the right of +1, which is +1. So the two one-sided limits both exist, but they don't equal the same number. So the two-sided limit, let's go with a capital D, capital N, capital E, it does not exist. So we have the graph of the absolute value function. Let's consider alongside that, or below that, the graph of its derivative. A very helpful exercise, I think, to see the connection between the graph of a function and the graph of its derivative is just to look at the graph, not so much the expression defining the function, but look at the graph and see if we can graph the derivative, the function that tells us the slope at any point. Well, it's going to be undefined at 0, but if we pick any positive number, the slope all along here, slope is 1, the 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 slope is 1. So it's going to be 1 all the way to the right. This is f of x equals the absolute value of x, and this is y equals f prime of x. Pick a negative number. I want to know what's the value of the derivative. Well, you look at the graph of the function. The slope is -1. Whoops, the slope is -1, -1, -1, -1, -1, -1. So it's constantly equal to -1. And hopefully this jives with what we just did in evaluating these two one-sided limits. If we look at this expression, if we're trying to evaluate absolute value of delta x over delta x as x approaches 0 from the left, it ends up being the limit of -1. X is approaching 0 from the left, and we get -1. If we approach from the right, we get +1. So the two don't meet. They miss each other like that. And so the two-sided limit does not exist there. So it's not differentiable at 0, even though it's continuous at 0. And the takeaway from this is that when we're looking at a graph and there's a sharp edge, if we've got a graph that looks like this, and then something like, it doesn't have to be a right angle, but it can be just a corner, something like that. I don't know, you might not cut yourself on that, maybe it's not all that sharp, but it goes from being a certain value to being another value, and it misses the values in between, right there at that point. So it's not a continuous transition from one value, the slope from one value to the next. And as far as the graph is concerned, the graph is not smooth. If it's got an edge to it like that, then it's not going to be differentiable. So this is a point of non-differentiability, if I can spell it. And other examples would be a cusp, something like that. It's not going to be differentiable right there at that point. Now, there are cases when the graph itself could be smooth, and I think example 8, were we to do it, I think actually could give us something that looks like this. If we have y equals the cube root of x, I believe the graph does something like this, something like that, and actually the slope of the tangent line is undefined at 0, and it's what's called a point of vertical tangency. And if the slope is undefined, then the derivative is undefined, because the derivative is the slope of the tangent line. So that's another situation where it's a point of non-differentiability. So if there's a corner, it's not differentiable there. If there's a cusp, if there's a vertical tangent line, even though the function itself may be continuous, the derivative may not exist at that point. I think that's kind of the takeaway from an example like this. So maybe
it may not exist. It could still exist.
If there's a point of vertical tangency, it doesn't exist.
Okay.
If there's a corner like this, I really should say that it doesn't exist. If there's an abrupt is the word I was searching for, an abrupt transition in the slope. Now it's possible to piece two functions together. You could have a parabola, and then you could go off and be a straight line from that point on, something like that. As long as there's not if you look at the slope that leads into this and the slope that leads into that, if they're approaching the same number, it's a smooth transition, then it could be differentiable at that point. But if there's a corner, it's not going to be differentiable. There. So a passing glance at example 8. Maybe just look at the result here. This is the f of x equals the cube root of x, and the function itself has all real numbers in its domain. You can take the cube root of positive numbers, you get positive numbers. You can take the cube root of negative numbers, you get negative numbers, and take the cube root of 0. So that function is continuous and has all real numbers in its domain. But if you look at the expression after we show all this work, look at the final answer, 1 over 3x to the 2/3 power. If you substitute 0 for x, you get 0 in the denominator. And that's because there is a vertical tangent line there right at 0, so the derivative is undefined at 0, even though the function is continuous there. So without having to suffer through that entire example, that's really the point that I intended to convey there. Let's look at the beginnings of some shortcuts for evaluating derivatives of functions. A few words about notation. We want to look at several different ways of denoting the derivative. When we're talking about the function that expresses the slope of the tangent line of a function in terms of x, that is the derivative, but the various different ways of denoting it. If we have the function f of x equals 3x squared plus 17, the derivative that can be found, f prime of x, can be shown to equal simply 6x. And 6x would, if we had a point on this graph of y equals 3x squared plus 17, and we substitute its x coordinate for x, the slope would be 6 times the x coordinate. It's basically what we're saying. Sometimes when we're considering the derivative, rather than thinking of it as a function, we'll think of it as an expression that defines a function. So rather than going with the left-hand side, f of x equals 3x squared plus 17, we'll just focus in on 3x squared plus 17. Let me put it right there. 3x squared plus 17. And what we'll say is we would like to differentiate that expression. Now what we're doing is we're finding an expression that would define the derivative of that function when we do that, but we're not really calling it f of x. We're just thinking of it as an expression that, if we could think of a good name for a function, it would define that function. When we do that, we need notation that says the derivative of this expression with respect to x. It might have other variables in there, or unknown constants. If it were ax squared, maybe a is just a constant, but it's unknown, so we're wondering, what's the variable? Is it a? Is it x? So we need to know the variable with respect to which we're differentiating. So we say it like this. We put what looks like a fraction, d, in what looks like the numerator of a fraction, and dx in what looks like the denominator of the fraction, And when we say that, what we say is d dx. We don't say d over dx, but it's d dx. This is what's called a differential operator, and it indicates the derivative of. Now, you never want to say, I guess I should copy this so I can write on it. Scroll down just a little bit and I can copy a little bit more. You never want to say d dx equals. You don't want to say d dx equals, because d dx never equals anything. It's like saying the square root equals, or the square root of, and you're just waiting for the object of the preposition. Well, what are you taking the square root of? If you say d dx equals, well, d dx is not a quantity, but it's just a set of instructions that tells you to take the derivative of some other quantity. So d dx is the derivative of, well, we're waiting to find out. D dx of 3x squared plus 17 means the derivative of the expression 3x squared plus 17. 6x would define the derivative of the function f of x equals 3x squared plus 17. Now, if we want to go ahead and talk and give this expression a name, y equals 3x squared plus 17, and you pick another variable and denote that expression, let y equal 3x squared plus 17, then what we can do is this. d dx of y equals d dx of 3x squared plus 17. On the right, we do the calculation and we come up with the expression 6x. And on the left, to have a quantity that will denote the derivative of that expression with respect to x, since we've called it y, we say dy dx. So the derivative of y with respect to x, we'll use the notation dy dx to denote that. Now it is appropriate, just like I've done here, to say dy dx equals a particular expression. d dx never equals anything, but dy dx is the notation we use to indicate the derivative of an expression that we've denoted as y in terms of x. So dy dx and f prime of x are being used in exactly the same way. So if the problem says find f prime of x, it means find the derivative. If it says find dy dx, it means find the derivative. And sometimes, although I use it less frequently because sometimes the independent variable gets lost in the mix, sometimes you can simply say y prime equals 6x. If y equals 3x squared plus 17, y prime is sometimes used to denote that. So just notation, and we'll see this notation a little bit more when we take the derivative of the derivative, which is called the second derivative. But for now, we've just got one derivative inside. Now to the shortcuts. At the top of the page, top of the notes, I wrote that limit definition again, and if we can avoid that, we will avoid having to take the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0 to find the derivative. We do that in a few cases, and then we build on that, and then we look at some shortcuts for finding derivatives of commonly used expressions. So the first one is the constant rule. This one hopefully kind of is intuitively clear because of the comfortable nature of the graph of a constant function. If we've got a constant function f of x equals c. So there's the point, there's the x-axis, there's the y-axis, there's the point 0, c, and here is f of x equals c. If I pick a point, any point on this graph, and then consider the tangent line, what's the slope of the tangent line? 0. It's the slope. It's the same as the slope of the line itself, the slope of the graph. And if you have a linear function, the slope of that line is the slope of the tangent line. So f prime of x is going to be 0 for any constant function. So our first theorem is simply the constant rule. The derivative of a constant function is 0. So if we want to find the derivative of a number, like d dx, I could do this in a couple of ways, and I probably should. If we have f of x equals -3, f prime of x equals 3, or if I just have d dx of -3, and that's 0. So the derivative of a constant equals 0. That's what we're saying there. And that'll be important, although hopefully it's not too difficult to see. Now the power rule is considerably less intuitive. Its proof would take probably a little longer than we'd want to spend, and would involve the use of the binomial theorem, because we'd have to do something like this. Maybe I could set it up, but just not follow through with it. The limit as delta x approaches 0 of, and I would take the expression x to the nth power, and we'd have to talk about x plus delta x to the nth power minus x all over delta x. Now that expression would look differently depending on, depending on the value of n. If n equals 2, we know how to square x plus delta x, but if n equals 3, if n equals 4, then we're looking at x plus delta x times x plus delta x times x plus delta x times x plus delta x. It's a mess, but we know you can use the binomial theorem, and the binomial theorem is used in the proof of this. Well, make a long story short, when you take the appropriate limit, what happens is that you get n times x to the n minus 1. So you see two things happening in a particular order. The first thing is if we have the derivative of x to the n comes out in front, and it looks like that. And then we subtract 1 from the exponent, and it looks like this. So if we wanted to take the derivative, but I have to be careful here because we haven't talked about the sum rule or the difference rule yet. So I can just do this. If I want to say d dx of 3x squared, I haven't talked about the constant multiple rule yet either. Sorry, my bad. If I want to find d dx of just plain old x squared, how about? This fits the x to the nth power. The 2 comes out in front, and we have to subtract 1 from the exponent. So 2 minus 1 is an invisible 1. How about that? So we get 2x there. So if we have the graph of, and let's see, I wonder if I saved it. Let me see if I saved it. The hastily thrown together GeoGebra worksheet that I did during the break yesterday. Let me double check that there's. If we go simple here, x squared for the derivative, then.
Did you want to turn your video back on?
Oh, I did. I unpaused it. Yeah, thank you. Unpaused it, and do you see the line? I guess what's got me uncomfortable here is the grid. Let's go 1 to 1. That's a little bit better. Do we see the line y equals 2x? I'm going to delete that. Y equals 2x? Does this look like y equals 2x here in red? Yeah, there it is. Y equals 2x. So if we look at the graph, and as the graph moves, and that other line was just, I don't know why it was there, but I wanted the slope of the tangent line. Basically, the equation of the tangent line. Basically, what I wanted was y minus, and the derivative is denoted by f prime here. So y minus this this point right here is a f of a, so when y minus f of a equals f prime of a times x minus a. And I wanted that to be the slope of the tangent line. And that the slope of that line right there is equal to the y coordinate that's on display right here. So right now the slope of that line is 2. And if I go there, the slope of the line would be 4. If I go all the way down, well, right there the slope of the line is 1.2. If I go there, it disappeared into the x-axis, sorry, but the slope of the line is 0, and the y coordinate of that point is 0. So we'll look at another one of those in a little bit. So the power rule. More examples of the power rule can be found in example 2. These have a lot more going on than y equals x squared. F of x equals x to the 35th power. If we were using the definition, we would need to take x plus delta x at some point and raise it to the 35th power. And that's just ridiculous and unnecessary. But if we want f prime of x, it's going to be 35 x to the 34th. So the 35 comes out in front, and then we reduce the exponent by 1. Want to be careful when applying this power rule, because we need to write the expression as x to a power. And here we've got the cube root of x squared. So this is x to what power? 2/3, yeah, x to the 2/3. So sometimes we have to simplify it a little bit so we can see x raised to what power. So g prime of x, exponent comes out in front, and then we subtract 1 from the exponent. 2/3 minus 3/3. Would it be negative 1/3? No, negative 1/3. And then probably want to write the final answer so that it doesn't have a negative exponent. In fact, probably want to write the final answer so it involves a radical, because the original expression involved a radical. So a couple of steps. G prime of x equals 2 over 3x to the 1/3. Negative exponent, slide it down to the denominator and change the sign of the exponent. It becomes positive. And so g prime of x equals 2 over 3 times the cube root of x. There we go. So this would be the derivative in this case. And h of x, although we have an x to the 4th power, this is not in the form of x raised to a power. It's 1 over x to a power, and so we can't apply it until we write it as h of x equals x to the negative 4. Then we can apply it. So h prime of x,
So negative 4.
Negative 4,
X to the negative 5th.
x to the negative 5th. And since the original, usually it's a good rule of thumb not to leave any negative exponents in the final answer. But since the original didn't have any negative exponents, it was written as a fraction, probably a good way to go for this one. So negative 4 over x to the 5th, yeah. Just like that.
So would we get it wrong if we left it in the step above?
Not unless I specifically say don't leave any negative exponents in the final answer. I think I would give credit for this. It's maybe a little bit nicer if you're writing solutions for a textbook that you've authored. You probably want to not leave any negative exponents. But if it's your textbook, hey, you want to leave negative exponents in the final answer. That's fine. Here we go. Constant multiple rule. I tried to be careful in the previous example to have just x raised to a power, not 5x raised to a power, or 3x raised to a power, as I almost did. Constant multiple rule, and I'll go with both this and the example. If f is a differentiable function at x and c is any real number, then if you form a new function by taking f of x and multiplying it by a constant, you can imagine what it does to the graph. You know, it just stretches the graph. Stretching the graph vertically is not going to alter its differentiability. If there wasn't previously a corner, there's not going to be a corner by just stretching it vertically. And if there wasn't previously a vertical tangent line, just stretching it by multiplying by c is not going to cause there to be one. So CF is going to be differentiable, and we can obtain the derivative by taking the derivative of f and multiplying it by c. Basically, the derivative of a constant times a function is equal to that constant times the derivative of the function. Another way of looking at it is the constant basically can be passed through, or up and over as I've drawn it there, the derivative. You can pass the constant through the derivative. You can't pull an x out of there, but if the constant does not depend on x, you can pass it through there. So in this case, if we could find the derivative of x to the negative 7th power, and we multiply that by 3, then that would be the derivative of 3x to the negative 7th. So I'm going to do this in gory detail for the 3x to the negative 7th, and then at some point someone will suggest, rightly so, why not just multiply the negative 7 by the 3? And of course, in practice, after this example 3a, that's what we'll do from that point forward. But I feel like I need to show it without doing that first. So to find the derivative of this, I've got y here instead of f of x. I'm trying to mix it up so you're comfortable with different notation. F prime of x in one example, dy dx in another example. So it doesn't leave you wondering, what does he mean by that? Well, in both cases, I mean, find the derivative. Dy dx equals, let's say it like this, d dx of 3x to the negative 7 using the constant multiple rule. The 3 comes outside, so it's 3 times d dx of x to the negative 7. So we find the derivative. I guess it'll take a couple of steps to find the derivative of x to the negative 7. This is 3 times negative 7 x to the negative 8. And now with the d dx gone at any time, we feel like multiplying by 3. Of course we can. This equals negative 21 x to the negative 8, which then we could write as negative 21 over x to the 8th. Now, if we were to do a few of these, I'm just going to do one and make this observation. You can see that if we just take the negative 7 and multiply it by the 3, we get the negative 21, and then reduce the exponent by 1. So long as you know that we're applying the constant multiple rule to enable us to do that, it's fine. We can do this every single time. Multiply that exponent by the coefficient, and then we don't have to include these extra steps in the middle. So I'm going to go ahead and do that with the b part, dy dx. If we multiply the 4 by negative 8, negative 32, reduce the exponent, and we get x cubed, yes. And the next one, let's see, probably want to work on that a little bit. Y equals 5/3 x to the 1/2. So dy dx equals 1/2 times 5/3 x to the negative 1/2. Subtract 1 from the exponent. And so dy dx, and I do 2 or 3 things at once. A lot going on here. Probably I should say 5/6 x to the negative 1/2, and then say that's 5 over 6 x to the positive 1/2. And while I'm at it, 5 over 6 times the square root of x. This would give us an expression for the derivative of this function.
So we need to have like dy dx equals 5 over.
That would be good in the final answer. dy dx equals 5 over 6 times the square root of x. I just ran short of space, that was all. Yes, that's good. Good form to have it there. Or y prime equals 5 over 6 times the square root of x. Example 4 is all about the algebra. All about the algebra. How can we best simplify these and get them to the point where we can actually take the derivative? So each of these we want to get it to the point where it's a constant times x raised to a power. If we write it as a constant times x raised to a power, then we can apply a combination of the power rule and the constant multiple rule, and we can find these derivatives. First one, in fact, I'm tempted just to do the algebra with each one first and then come back and find the derivatives, just so the point is writing each one as a constant times x to a power. The first one is 7/4 times x to the negative 3. Y equals that. Not dy dx, of course. No derivative yet. But just y equals 7/4 times x to the negative 3. Then we're in a position at this point to take the derivative. The next one, y equals, well, the 4x is cubed, so we've got to go ahead and clear the parentheses. 7 over 64x cubed. So a little bit different, but not too much different. Y equals 7/64 x to the negative 3. Then we can take the derivative of that. The c part is actually quite nice because we have the negative exponent starting out in the denominator. In this case, y equals 7/4 times x to the positive 3. And we can take the derivative of that. And the d part, y equals 7 times 4x quantity cubed. Now what that means, the entire quantity 4x is raised to the negative 3, so that means the entire quantity 4x should be shifted up to the numerator, and I should change it to positive 3. Then we cube it, and y equals 7 times 64x cubed, and let's see, 420 plus 28, 448. So y equals 448 x cubed, and then we can take the derivative of that.
Why didn't we just pull the x out like we did for the rest?
For this d part, because of the parentheses, and because we had a negative exponent on the parentheses. I suppose I could have worked in the denominator first. I could have said 64x to the, well, I would have had to say 4 to the negative 3 down in the denominator, and it would have been 1/64. 1/64 x to the negative 3 down the denominator, and I was just a little uncomfortable with that. So rather than having to deal with the complex fraction, I just went ahead and took the whole thing up to the numerator, and it made it quite nice because it made the exponent positive once you moved it up to the numerator. And then, how do you feel about those derivatives at this point? Do a little bit of algebra. It shouldn't be too bad. Let me see if I can do it. dy dx equals negative 21/4 x to the negative 4. So I guess there is a little something to this, because then I want to write it as negative 21 over 4x to the 4th. So there's the task of taking the derivative and then cleaning it up a little bit and expressing it with a non-negative exponent. So final answer to that part, dy dx equals 21, very similar here, 21/64 x to the negative 4. So dy dx equals, whoops, I left off the negative, didn't I? So sorry. Negative 21 64ths x to the negative 4. So negative 21 over 64 x to the 4th dy dx equals 21/4 x to the second power. Subtract 1 from the 3 to get 2. Not too much more simplifying to do there. And the last one, dy dx, if I can multiply 3 by 448, I don't think I can. 14? 1344 x squared. Yeah. Parentheses, negative exponents, where they're positioned in the denominator, can be tricky. So make sure you simplify it, clear the parentheses if necessary, and write it as a number times x to a power. And then you can apply a combination of the power rule and the constant multiple rule. Here we have the sum and difference rule. So to this point, I felt a little uncomfortable trying to use these rules for the derivative of that 3x squared plus 17 that we looked at right at the beginning of class. But I think once I state these, and actually the proofs are not that difficult. If I felt like I just had tons and tons of time and we didn't need to spend time talking about what to expect on the test, then I might try to prove at least one of these. Later, a week later, I do want to try to prove the product rule and or the quotient rule, so I'll save the proof for then. I'll just state these. Derivative of a sum of two functions, or derivative of the sum of two expressions, which can be used to define functions, is equal to the sum of the derivatives. Now to apply this, each of the functions needs to be differentiable at x, but if each function is differentiable at x, then the sum function f plus g, the difference function f minus g, are both differentiable, and you can find the derivatives just by evaluating the derivative of f, finding the derivative of f, finding the derivative of g, and adding them together. It's exactly what we would hope for in a derivative rule that enables us to find the derivative of the sum of several expressions. Turns out that the derivative of a product, f times g, does not, in general, equal the product of the derivatives. There's something called a product rule, something called a quotient rule that we'll use for those derivatives. But the derivative of a sum does equal the sum of the derivatives, and the derivative of a difference does equal the difference of the derivatives. And its application is very straightforward. If we have f of x equals 3x to the fourth plus 6x squared, if we wanted to write this as a number times x to a power, I don't think we could do it. But if we could break this, that's a number times x to a power, that's a number times x to a power, so we can differentiate them individually. So I'm going to write this, let's see, using as much detail as possible, but in general, at a glance, you do this and you just write down the answer. You don't have to do all the steps. So what we would say is f prime of x equals d dx of the sum, 3x to the fourth plus 6x squared. Then invoke the sum rule. F prime of x equals d dx of 3x to the fourth plus d dx of 6x squared. Now, if we were really taking our time, we would at this point invoke the constant multiple rule and pull out those constants, but we've been there, and we're not going to do that. Multiply the 4 by 3 and get 12, so that's 12x cubed, subtracting 1 from the exponent. Multiply the 2 by 6 and get 12, subtract 1 from the subtract 1 from the 2, and we get x to the invisible 1. In practice, of course, we look at 3x to the fourth and we do what we just did with the 3x to the fourth. We look at the 6x squared, we do what we just did to the 6x squared, and we don't write the two steps in the middle. We just write down the final answer. So the derivative of the sum is equal to the sum of the derivatives, and we call this differentiating term by term. So we look at this term, find the derivative, write it down. Look at this term, find the derivative, write it down, and the final derivative is the sum of the individual derivatives of the individual terms. All right. Before the break, let's see if we can look at the derivative of sine x or the derivative of cosine x. The derivative of sine x has been done for us. I feel compelled maybe to show you how this works for the derivative of cosine x rather than just kind of talking through this and pointing. So if we've got, let me zoom out just a little bit, maybe a lot. Okay, it's all there. If we've got these angle sum formulas, we can probably use them just like they've been used here to find the derivative of sine x, to find the derivative of cosine x. So what I want to do is something that looks very much like this, except I'm going to see if I can find the derivative of cosine x, whereas the derivative of sine x has been done for us. Oh, let's look at the punchline. Derivative of sine x, cosine x. How about that? Wonder what the derivative of cosine x will be. Let's see. d dx of cosine x equals the limit. I said I would use this limit definition sparingly. I'm going to have to use it for this one, going to have to use it for a logarithmic function, but hopefully not for too terribly many more than this. Cosine of x plus delta x minus cosine of x all over delta x. Now, I must say this, because we're going to use these limit formulas, limit of sine delta x over delta x as delta x approaches 0. The way we demonstrated that limit using the triangle inside of a sector inside of a triangle proof that we did that day, we were assuming that x was measured in radians. So the derivative of sine x, derivative of cosine x, we're assuming that they're measured in radians. So if the angle is measured in degrees, we're going to be off by a factor of pi over 180, 180 over pi, something like that. So in order for these derivatives to work out just right, the independent variable must be measured in radians, not degrees or some other manufactured contrived unit. So this is going to be the limit as delta x approaches 0 of, all right, going to use this angle sum formula for cosine. Cosine of a plus b, cosine of x plus delta x, and I'm going to write this cosine x cosine delta x minus sine x sine delta x, and then we've got the minus cosine x there on the end, so minus cosine x. This equals, and already I need to be thinking like this really is going to have the feel of those limits that we evaluated in building the trig functions, where x was approaching pi over 6 or x was approaching pi over 3, and we had to do the substitution, let u equal x minus pi over 6 or pi over 6 minus x, that sort of thing. It should have that feel. So I want to get the cosines together. So this is going to be the limit as delta x approaches 0 of cosine x times cosine delta x minus 1 minus sine x sine delta x all over delta x. And you see what's going on there. Basically, I take this expression and this expression and factor out a cosine x. When we factor out a cosine x, we get cosine x, cosine delta x minus 1 on the inside. All right, if I suspect that the limits actually exist, I can write well, whether the limits exist or not, I can write this fraction as the difference of two expressions. So it's the limit of cosine x times cosine delta x minus 1 over delta x minus sine x sine delta x over delta x. Regardless of whether the limit exists or not, it's a valid way to rewrite that fraction, breaking apart and keeping the denominator delta x. Now I want to say what I was going to say. If I believe the limits exist, then the limit of the difference is equal to the difference of the limits. So I can say this equals the limit as delta x approaches 0 of cosine x times cosine delta x minus 1 over delta x minus the limit as delta x approaches 0 of sine x sine delta x over delta x. It's yet to be seen if those limits exist, but I believe they do. And now, as delta x approaches 0, x itself is not going anywhere. It's just hanging around at x. X might be some number. It could be the cosine of pi over 2. X does not depend on the value of delta x. So the expression cosine x here and sine x here can be passed through those respective limits because they don't change when delta x changes.
So they're like a constant.
They're like constants, exactly. So it's going to be cosine x times the limit as delta x approaches 0 of cosine delta x minus 1 over delta x minus sine x times the limit as delta x approaches 0 of sine delta x over delta x. And then we evaluate limits. We go back to those two key limits from that section where we did the triangle inside of the sector inside of the triangle proof. And we said as delta x approaches 0, or x approaches 0 at that time, but in this case delta x is approaching 0, the value of this limit right here is what? 0. So it's cosine x times 0 minus sine x times what? 1. So cosine x times 0 is 0, so what we get is, might be a tad disappointing if we were hoping for sine x, it's negative sine x. So the derivative of sine x is cosine x, but going back we have to have a negative factor. Derivative of cosine x is negative sine x. Nonetheless, they have a nice relationship with each other in that regard. Okay, we just did that. At that point, though, well, we should take a break, is what we should do. But at that point, we should look at some examples of derivatives involving trig functions. So perhaps I'll do that before we jump into the rectilinear motion when we get back. But let's pass this up, I guess. See if I can sketch this graph.
Oh, yeah. I had them all before. Wow, we have until we have the number of those on that. For what? For college. You finish applications yet? Well, with UWF, they haven't even posted their applications yet. A few haven't. Where'd you apply? I'm basically going to apply UWF and UCF. Because I'm pretty set on UWF, but I just want balance for flexibility.
If a particle travels at a constant velocity, say 60 miles per hour in a particular direction, we can express the distance or the particle's location in terms of the time that has elapsed. For example, if S of t equals 60t, this could be an indication of the particle's position after t hours, where it's 60 miles per hour times the number of hours that have elapsed. In this case, it's a linear function, so after 1 hour, then the particle would be 60 miles on the positive side of its originating point. And then after 2 hours, 120 miles on the positive side of that. After 3 hours, 180 miles on the positive side of that. Now, the question I guess I would ask is, what can we make of the slope of this line? What is the slope of this line? 60? And if we consider it in terms of the units, miles on the vertical axis, hours on the horizontal axis, the slope would be 60 miles per hour, which is customarily what we think of as the speed, or if the direction is also a factor here, the velocity of this particular particle, vehicle, or whatever it is. So the slope of this graph is going to represent the velocity at any point if the position function is curved. That is, if the velocity is variable. Maybe it's undergoing acceleration, so it starts off at maybe a velocity of 0, and it gradually increases its velocity and has a curve that looks something like this. Then at any point, the slope of the tangent line could be regarded as the instantaneous velocity of the particle. So we want to consider a couple things: average velocity and then instantaneous velocity. If we pick a particular point on a graph, and all of a sudden it feels like a curved graph would be more appropriate for this. If we have something like this, if we pick a particular value of t and then go forward in time a little bit, could go back in time if delta t is negative, but imagine going forward in time, delta t to a point, t plus delta t, and considering another point on the graph right there. If we look at the slope of the secant line, we've kind of been there and done that, talked about slopes of secant lines. This would be the average rate of change of the particle on that time interval, average rate of change of the position of that particle on that time interval, so that would be the average velocity. Basically, it's the change in the distance divided by the change in time, and it can be calculated by f of, let's see, this is t plus delta t f of t plus delta t, and this is simply t f of t. So if we apply the slope formula to that, then we get this particular difference quotient. If we calculate the limit of delta s over delta t as delta t approaches 0, kind of drive this point down toward this point so that the secant line approaches the tangent line, then we can refer to this as the instantaneous velocity, and that's going to be the slope of the tangent line. So the slope of the tangent line to the graph of the position function is going to be the velocity function. So if we have a function such as this, s of t, let's go back to the linear case, s of t equals 60t, and we take the derivative of that. Now, I don't think we had any examples where it was the variable raised to the first power. We can apply the power rule to that. V of t is going to be how we'll denote S prime of t, and in this case, it's 60. So the derivative of the position function is going to give us the instantaneous velocity. Now I have an example, and I may take a moment to look at the example, but just kind of to get a look at this, let me think in terms of meters per second with some one-digit numbers rather than double-digit and triple-digit numbers.
Okay, hold on. Where
Yes.
did the t go?
We didn't do an example of that earlier. 1 times 60 is 60. Then we reduce the exponent by 1. Yes. Yeah, the first time you see that, it's weird that it just vanishes, but it's t to the 0 power. So we don't have to write the t. Another way to think of it is it's linear, so it's just the slope.
Okay.
That's another way to think of it. But the power rule, we subtract 1 from the exponent. So I'm going to hope this can be helpful. What we see is 3 graphs, and we may only have time to talk about the 2 on the right today. We see 3 graphs. The one on the far right is what I'm going to regard as the position function. Tells where the particle is with respect to some 0 point. How far on the positive side of it is. If it's above, it's going to be how far on the positive side of 0. If it's below, it's going to be how far on the negative side of 0. So as I move the slider, basically seconds are ticking away, it starts right at the origin, right at this point. And then we're going to let 1 second go by and see where it is after 1 second. After 1 second, the particle has reached a point where it's 3 units on the positive side of the origin. So what's going to be more comfortable? If we think of the particle as moving to the right and to the left, or if we think of the particle as moving up and down? What's more natural?
Up and down.
Up and down? Well, visually on the graph it's moving up and down, so maybe that's better. So the particle starts at 0, and then 1 second goes by, and it's reached a point 3 units above that. And then another second goes by, and it's only gone up 1 more unit, so now it's at a point 4 units above the 0 point. And then the clock keeps ticking, but what's happening is the particle has basically slowed to a stop, and now it's going to come back. So it's going to go for another second, and a second later, it's back down only 3 units above the 0 point. And then we're going to just let 1 more second go by, and after 1 more second, the particle is back at 0. So that's what it does. In 1 second it goes up 3, and the next second it goes up 1, in the next second it goes down 1, and the next second it goes down 3. Now throughout its journey, what's happening is the velocity of the particle is going from a positive 4 meters per second down to a negative 4 meters per second, because we can track the velocity by looking at the slope of the tangent line to the graph of the position function. Let's start back here. I think we can look at the tangent line. The tangent line is this broken line here, and calculate the slope just kind of by looking at it. It looks like rise over run. It goes, up 4 and 1 to the right. So the horizontal units are seconds, and the vertical units are meters. Some appropriate unit of distance. I'll just call them meters. So if we divide 4 meters by 1 second, that's 4 meters per second. So initially, the velocity is positive 4 meters per second. Now, velocity has direction. So positive, if the particle is moving up and down, we're going to say positive is up. So initially, it's going 4 meters per second straight up. Now, something's slowing it down. Now this is it's only slowing down at the rate of about 2 meters per second each second, so it's not Earth's gravity. Earth's gravity is going to slow it down more than that. But something slowed it down, slowing it down at 2 meters per second each second. So if we let another second go by, and it's right there, what's the slope? If we're right there and we look, we go up 2 and 1 to the right, so 2 meters divided by 1 second, it's only going 2 meters per second. And then we let another second go by. Whoops. What's the slope now? 0. So at the beginning it's going 4 meters per second, and then 2 meters per second, and then 0 meters per second. It's basically stationary at this point. And then the velocity continues to decrease because a second later, what's the slope? -2. That means it's headed down. It's headed down at the rate of 2 meters per second. If you think 2 down, 1 to the right, so it's going to be a slope of -2 meters per second. And then another second goes by, and it's it's speeding up, heading back toward the initial. Like I said, it hits if there's something solid where the initial point was. It hits it at a rate of 4 meters per second. Now we can calculate the velocity at any point by examining the slope of the tangent line, or we could take the derivative. Now this parabola that you see here is, if you use t's instead of x's, it's s of t. GeoGebra doesn't like to use t's for the independent variable. But it's s of t equals -t squared plus 4x. If we take the derivative of that using the power rule that we've used, it's going to be -2x plus 4, and that's the graph of this straight line right here. This is the velocity function in the middle. The velocity function starts at 4, and then it's 3, and then it's 2, and then it's 1, and then it's 0, and then it's -1, -2, -3, -4. So one way of tracking the velocity is to keep track of the slope of the tangent line. Another way of tracking the velocity is to find the derivative and just look at the velocity function right there. So this is kind of what's going on as the particle is, its velocity is decreasing by 4 meters per second each second. Let's see, I don't know that much more needs to be said, except if you want to take it one more step and you want to ask yourself, what function describes how the velocity is changing with respect to time? What function are we talking about in that case? Acceleration. See, throughout the process, the velocity is -2 meters per second, and so that's the slope of this curve. If you look at the slope, it's 2 down and 1 to the right, so that would be -2 meters per second. So that's the constant velocity. And so if you look at the acceleration, this is the acceleration function. It's a horizontal line 2 units below the x-axis, so it's a constant -2 meters per second. So this is kind of, we'll look at this again at some point, but that's kind of because you can see them changing at the same time. It was helpful to me when I looked at that. The example that I had some other questions comparing average velocity and average speed, and then instantaneous velocity. I'm going to look and see what specific review problems I have that touch on that topic. And I really don't think that I have I don't think I have any in section 3.2. Is there anything involving rectilinear motion, section 3.2? 21? we've got the horizontal tangent lines. That's an interesting one for a homework problem. I don't think it'll show up on the test, but that is kind of an examination of the discriminant. You take the derivative of that and then find the discriminant. But it's probably appropriate that I don't have any rectilinear motion problems on this review or on the test, because I just feel like it's late in the game when I'm actually mentioning it. So let's look at the review. There'll be more to be said about rectilinear motion in the future, but let's look and see specifically what you should pay attention to as you prepare for the test, and what you might not need to pay attention to. I think section 2.4, problem number 1, about where is a function continuous. This piecewise graph, it's good to have a picture of it in your mind, and then you can see if a function is continuous on a particular closed interval or half open interval or open interval. Case in point, from negative 2 to 3, it is continuous on the open interval from negative 2 to 3, because it's continuous at 1, and the other places there it's defined by these polynomials, which are continuous functions. We can include the negative 2 or not. It's continuous from the right at negative 2 because it goes up to that point where it's defined, and we have a solid dot right where it should be. Of course, it's not continuous at 3 because it's not even defined at 3. So, what did you circle in that case? You circled the... You circled that one, and also that one, but not J, and not L, right? Because those include the 3. So a good one to connect the picture of a graph with whether or not it's continuous on a particular interval.
Do we actually have a picture for that one on the test?
That's a good question.
Or can we
I'm trying to remember if I
draw our own.
I think maybe I would want you to draw your own picture for problems such as that. I'll give you I have to do one or the other. Either I've got to give you the picture or I've got to give you the function there. Probably give you the function. The rules defining the function. Problem 2 is good. Factor the numerator, factor the denominator. You can decide whether it's continuous or movable discontinuity, jump discontinuity, or vertical asymptote. I don't think number 2 has any jump discontinuities. 3 probably does. Piecewise function likely has a jump discontinuity, among others. How did problem 4 go for you? Is that a good one or a bad one? Did you find the values of k that made this happen? And were you able to sketch the graphs once you found the values of k? Did it take a while? Okay, maybe I can find a similar one on the test that won't take as long. But I want it to take a while. 5, the intermediate value theorem is nice. Basically evaluate the function at the endpoints. If you get opposite signs, then you know, since the function is continuous, it guarantees the existence of at least one 0 in that interval. If you don't get opposite signs, then it tells you nothing, because maybe there are bunches and bunches of zeros in that interval, or maybe none at all. You don't know, but either it guarantees the existence of a 0, or it gives you no information about the existence of zeros. What you don't want to say is that it guarantees that there's not one. It's an existence theorem. It does not guarantee the non-existence of a 0 on an interval. 6, the B part is a bear unless you pass the function through the limit because it's a continuous function. If you'll say that that's f of the limit of g of x as x approaches 2, that's much nicer. You just find the limit of that expression, and for g as x approaches 2, it takes a little bit of work, but you can find it, and then you plug it in to the function of f. And that's not too tough. 7, looks like you, 7 is the one I tried at the beginning of class last time, wasn't it? That didn't go so well. Factor correctly the numerator and the denominator And I don't think a factor divides out, but then based on whether x is a little bit more than 2 or a little bit less than 2, you want to figure out, is this going to positive infinity or going to negative infinity? I believe it's one or the other, and you can make that determination based on the factors.
I think a factor is on number 7?
Number 7?
Yeah.
Mm-hmm. Does a factor divide out?
X minus 3.
The x minus 3's divide out? I don't remember. Maybe it did it not? Maybe it
That's
didn't.
what you have on your answers.
Uh-oh.